All right, this is section 6.6. We're going to look at the graphs of transformed sine functions and cosine functions. And we're going to be really looking at how these functions follow these transformations. Let's look at our basic function of f of x is equal to sine of x. And let's say I wanted to do f of x is equal to 2 sine of x. As I look at this function, this number here is going to multiply all of these values that I have here and spread them out in the graph. So if I look at my actual function that I have, let's take a look at what Geogebra gives us here. Here in my original green function, I have sine of x. And in my blue function, I have sine of 2x. We can see that it has the same amount of bumps, but that it gets twice as much for every value, meaning that right here, this value has an output of 1, and right here, this value has an output of 2, but right here, this has a value of half. I double that, I'm going to get 1. So it doubles the amount of value that I have. This value that I have here is called the amplitude. If you were talking and you want to make something sound louder, you would increase the amplitude of what you were talking about. So the higher the amplitude, the larger the wave is going to be separated. Now, if I decide that I want to multiply 2 inside, now we're looking at a horizontal shrink. And I'm going to take that and I'm going to change this. And what's going to happen is it's going to double the amount of bumps that I have normally with a normal sine function. The green normal sine function, I have 2 bumps per 2 pi. This one in here, I'd have 4 bumps per 2 pi. This is called the period. And the period represents the number of cycles that you have over 2 pi. So now to figure out the period, that's equal to 2 pi divided by whatever value this is, which in this case is equal to pi. If we look at our graph that we have in Geogebra, it goes through a complete sine cycle in 3.14. The next attribute I want to look at is called the vertical shift. I'm going to change this function here. I'm going to add 3 to it. Now, the vertical shift, where we have sine of x plus 3 in this case, is going to shift that whole graph up 3 units. So it takes all values that I have for sine here, and then it moves it up on the graph 3 units. We still have the same number of bumps. We still have the same amount of amplitude, if you will. We're just shifting it up 3 units. Now the last one we're going to look at is something called a phase shift. Now a phase shift moves the graph horizontally. Here in this case I did x minus pi over 3. And we can see what happened to that graph. Because it was negative here, it moved it in the positive direction. We learned this in our transformations back in chapter 2. So if we look at our graph, we can see that it shifted pi over 3 to the right. And pi over 3 is just over 1 here. So instead of starting at 0, it's starting at pi over 3, and then we've shifted it just a little bit. So we have these 4 attributes that we have when we're looking at simple trig functions. If we decide to put it all together, it looks like this. We have f of x is equal to a times the sine of x minus c plus d. A represents the amplitude. More importantly, the absolute value of A is the amplitude. Amplitude is always going to be positive in this case. I forgot B here. B gives us the period. And the period is equal to 2 pi divided by B, or 360 degrees divided by B. These are always positive as well, so we'll put absolute values around those. C gives us our phase shift. Now our phase shift is a little bit complicated because we actually have to do C divided by B in both of these cases. So the phase shift represents the amount of our horizontal shift, but you're going to have to take this C and divide it by B in order to get those values. Here we got C divided by B. That's if you're in terms of pi, or if you're doing 360 degrees. Depends if you're using radians or degrees in this case. That's when you would use that. D represents our vertical shift. And that's just going to be our value of D. That's easy to pick out. Okay, so you want to look at this, and you want to be able to look at this equation and find your amplitude, your period, your phase shift, and your vertical shift. All right, so now let's put it all together. Let's say we had the equation where we had f of x is equal to 2 times the sine of, let's do 3x minus pi over 6 plus 10. Here, our amplitude is equal to 2. And we pick that up right from here. Our period is going to be equal to 2 pi divided by 3. And that's going to be this value that we have right here. Our phase shift, that's going to be equal to pi over 6. And it's going to be the positive value I have here. Now I've already factored this out, so that makes it a little bit easier to pick it out. Our vertical shift here is going to be equal to 10. Let's look at an example where I have sine of, let's do 2x minus 60 plus 1. Here, our amplitude, without a number in here, we're going to assume the value of 1. Our period is going to be equal to this number. So it's going to be 2 pi divided by 2. That's going to be equal to pi. Or if you were in degree mode, you would do 360 divided by 2. That would be 180 degrees. Phase shift is going to be a little bit more complicated. We're going to do 60 divided by 2. Remember, that's going to be a positive value. If you were in radian mode, you would do, well, no, we're going to assume that we're in degree mode here. And then our vertical shift is going to be equal to 1. This should get you through section 6.6. If you have any questions, please use the Ask My Instructor feature and send me an email. And good luck. Thank you very much.